If we go ahead and think back to chapters 13 and 14 that we put together, we studied the effect of temperature and pressure on the volume of a constant mass of a gas. Again, we looked at the variables, Boyle's law, pressure and volume. We looked at Charles's law, volume and temperature. We looked at Gay-Lussac's law, pressure and temperature. And we could put them all together also. But in this chapter, what we're going to do is we're actually going to throw in that fourth variable that we talked about, which is going to be the number of particles. Also, we're going to end up closing off with all of our finishing stoichiometry that will now be able to include volumes of gases. At a given temperature, again, remember what we said, kinetic energy is going to be exactly the same. At the same pressure, again, we said that there are an equal number of particles. If I have two tires, one's filled with O2 and one's filled with N2, both have the same pressure. Again, they have the same number of particles. Again, when you start thinking about what we talked about and closing, we talked about that idea of molar volume. And we said they have the same number of particles at STP, 22.4 liters. Again, we said that if we take a gas and we put it at standard conditions, and they are equal volumes, we're going to again have 22.4. Again, that's Avogadro's principle. At equal temperature and equal pressures, equal volumes of gases contain the same number of particles. So what we're saying is volume 1 and volume 2 are going to be equal to one another. What we're going to say here is to represent the number of particles, we're going to say that's N. So what we can say then is N1 is going to be equal to N2. Again, talking about molar volume, that 22.4, what we can now do is go ahead and start looking at what we've talked about. We said that if we took pressure multiplied by volume and divided it by the temperature, we came up with some constant K. Again, that's that combined gas law that we just got done talking about. But we can also say K is going to be equal to N multiplied by some constant R. So again, if we go ahead and look here, K and K, what I can do is I can go ahead and substitute in. PV divided by T is going to be equal to NR. Again, I don't like denominators, so I can say that PV is going to be equal to nRT. Well, we know what pressure is. We know what volume is. We basically know what N is. We know what temperature is, but what is R? How do we calculate out R? Well, that's what we're going to do now. We're going to go ahead and solve for R. Solve for R at STP. So let's go ahead and look here. At STP, well, again, let's look pressure. Pressure, standard pressure, 101.325 kPa. Molar volume, again, we're going to take 1 mole of any gas at STP. And we said 1 mole of any gas at STP, that's 22.4 liters. Again, that number right there is just your molar volume. N. Okay, again, N was going to be our number of particles. If, again, you think about what I just got done saying, 1 mole of any gas at STP, so N is going to be 1 mole. R is going to be what we're solving for. Standard temperature, again, always Kelvin, 273 Kelvin. So basically what I'm going to do to solve for R, I'm going to divide by 1 mole. I'm going to divide by 273 Kelvin, and when I do that, of course, these variables end up canceling out. And if you take 101.325 multiplied by 22.4, essentially divided by just 273 Kelvin, what you'll end up with is 8.314. Units on this, kilopascals, liters, mole, Kelvin. Now, the one thing that I want to tell you, the key thing to this is going to be your pressure. Because as you go through and you start looking and reading chapter number 14, you're going to find out that there are different values for R. For example, there is also R can be equal to 0.0821. Now, units on that one, liters, atmospheres per mole Kelvin. The other one out there, R is going to be equal to 62.4 liters, millimeters of mercury mole Kelvin. I'm hoping when you look at this, you can see that the only difference comes right here in what your unit of pressure is. If we use kilopascals, it has to be 8.314. If we use atmospheres, it has to be 0.0821. And if we use millimeters of mercury, it has to be 62.4. Now remember what I've always said. For quizzes and tests, I'm going to drive things towards kilopascals. This is what you will need to know for quizzes and tests. I will not use any atmospheres. I will not use any millimeters of mercury. But realize there are going to be book questions into the chapter questions. They might give you atmospheres. And if they give you atmospheres, then all you have to do is for the value of R, right in here, plug in then instead 0.0821 if they would give you atmospheres. What I want to do is I want to go back into our PV equals nRT, because we can go ahead and actually solve for a couple other equations. And this equation right here is really just going to be the ideal gas equation. Ideal gas equation. And the reason why it's the ideal gas equation, again, it looks at the perfect setup, the perfect gas, which of course we know doesn't exist. We have real gases. But the other thing is it looks at all four variables together. It looks at pressure, it looks at volume, it looks at the number of particles, and it looks at temperature. Again, if you think back to what we used to do, again, if I gave you 0.891 grams of chlorine, and I told you, well, what I want you to do is I want you to convert that to moles. And basically, you would have done this, 1 mole, okay, chlorine 35.5, so you would have said 71 grams of chlorine. Well, really what you did is you took N, okay, was going to be equal to that mass. That's what I just gave you right there, mass. And really all you did is you looked it up on the periodic table, and that's your molar mass. So in reality, what you did was you took some mass, and what you did is you divided it by the molar mass. Well, notice what we have here. We have N. What I'm going to do is I'm just going to go ahead and substitute in. I'm going to take PV is going to be equal to, what I'm going to do is I'm going to end up putting in little m over big M, but really your R and T still end up on top. Doing your cross multiplying, what I end up with is PV molar mass, or big M, is equal to little m, which is just my sample mass, RT. So I've got that equation for the ideal gas equation. I've got that equation for the ideal gas equation. Again, this M right here, that M just represents molar mass. So if I tell you water, look water up and add up what its total mass would be. If I would tell you carbon dioxide, add up what carbon dioxide is on the periodic table. If I give you this M right here, that just means sample mass. If I went out and said that a scientist measured out 0.4 grams of a gas, if a scientist measured out 2.7 grams of a gas, that's just a sample mass. Okay, so again, big M is your molar mass, little m is going to be your sample mass. Well, the last thing I want to do is I want to go ahead and solve for our third ideal gas equation. What I want to do is I'm going to go ahead and isolate for M. Okay, so let's go ahead. PV big M equals little m RT. And again, if I want to isolate for big M, and again, you look here, it's P times V times big M. Opposite, or to get rid of those variables, I'm going to go ahead and end up dividing. So by doing that, my pressure and volume are gone. So what we have, and this is the way your book looks at it, molar mass is going to be equal to your sample mass multiplied by that constant R multiplied by that constant T divided by the pressure and the volume. Well, I'm hoping when you look at this equation, I'm hoping that there's something that maybe jumps out at you. And the variables right here, mass divided by volume, if I go ahead and pull those two variables out, mass divided by volume, I'm hoping that you'll remember that that's density. Okay, so what I can do now is I can say that big M is going to be equal to, well, we said that little m divided by V was going to be equal to density RT over P. And again, getting rid of your denominator, if I cross multiply, I'll end up with PM is going to be equal to dRT. And again, when I look at that equation, I want to think about variables. Density is going to be a mass over a volume. Well, again, your units for mass and volume, again, mass is going to have to be in grams. But when you think back to the R that we had, volume was going to be measured in liters. That goes back up to what we had up top here when we solved for R. Here was my unit for volume. So if I'm using the ideal gas equation, mass will have to be in grams, volume will have to be in liters. So if we revisit the equations, PV equals nRT. Units, pressure, kPa, for how I'm going to drive it. Volume has to be in liters. N has to be in moles. Temperature has to be in Kelvin. That's ideal gas equation number 1. Ideal gas equation number 2, we had PV big M is equal to little m RT. Pressure, kilopascals. Volume, liters. Molar mass. Molar mass is just going to be a grams per mole. Little m, that's just my sample mass. That's just going to be straight out grams. Temperature, Kelvin. And then the third one that we just ended up solving for. PM equals dRT. Pressure, kilopascals. Molar mass or molecular mass, grams per mole. Density, grams per liter. And again, temperature, Kelvin. Now again, I told you I'm driving everything towards kilopascals. If you would be given atmospheres or you would be given millimeters of mercury, obviously that changes your pressure and that changes your R value. Notice I didn't do anything with R because again, I told you I'm going to drive it towards 8.314.